the last time I was in New York, I had a cold, which is not the virus everybody's worried about right now, but it's still no fun to have a cold, of course. And it made me remember the time I was actually, about your age, a sophomore in high school, and my dad had told me about an experiment that he read where people saltwater gargled in the morning every day in the winter, and their chance of cold went down by like 40%. My dad cared a lot, and at that age, honestly, I thought he was kind of annoying, and you may think a little bit about that, your parents as well. But just see, the older you are, the smarter your parents become. So, anyways, he left me the recipe and said you should put 7 tablespoons salt in 8 ounces of water. That's how I read the recipe. So based on the last chapter test that we had on molar mass calculations, moles, stoichiometry, and molarity, what we're going to do is have you go ahead and calculate what the molarity of this solution would be. As a pedagogical aside, I like to do this not only to review, but if we were in a classroom setting, we do it by index card or iClicker, some way where they can anonymously submit their answer. Similar in a distance learning environment, we would try to have them anonymously submit an answer such that I have a way of checking and making sure we haven't left the class behind. And then by submitting anonymously, they don't feel like too much pressure to get something right or wrong. So we determined the molarity of this from the conversion factors and the periodic table, okay? And we found out it's about an 8 molarity solution in about 250 milliliters of solution. That's the saltwater gargle recipe my dad left for me, so I thought. Now, based on the definitions we went over yesterday, remember hopefully that solution is a homogeneous mixture of atoms, ions, and small molecules. There's going to be at least 2 parts to our solution. There's the solute, which is the element being dissolved, and it's always in a lesser proportion. And there's our solvent. Which dissolves the solute, okay? Or it's in a greater proportion. So in this example, you'll recall that and it's really common to have a salt, an ionic salt, as the solute in the solvent of water. So at this point in time, because I like to have students move at least every 15 to 20 minutes, either it's their visual gaze into one board or another person is talking, or they're physically moving. In the case of distance learning, they can certainly prepare this kind of saltwater thing at home, okay, which is why I included the English units. And then, of course, in the lab, we can do all kinds of, we have many more options here for something a little more sophisticated. Okay. But we would be making this and measuring it out. So here's roughly trying to make an 8 molar, 250 milliliter solution of salt water. We'll stir it a little bit. Okay. So as you're making this at home, or as we see this in the lab, and we stir it up, you may notice that not all of the salt is able to dissolve in the water. It has a limited, here's another definition that we went over before. It has a limited solubility. How much solute can we place in the solvent? When we look at this, as this kind of settles out, you'll see that some of the salt has dissolved or seemingly disappeared into the solution. Right? So chemically, what is going on here? Well, we have sodium chloride as a solid, water as a liquid, dissolving into sodium ion and a chloride ion. And these are called aqueous. Meaning they're dissolved in water. Aqueous ions are essential for life. Your life literally depends on aqueous ions. Okay? And the extent to which some things dissolve and some things don't dissolve determines a whole host of biochemical interactions. And I want to kind of emphasize that by taking a look at what's actually happening here. We have solid sodium chloride. You've all seen it. Okay? You could set it out on the countertop and it'll stay that way for 20, 50, or 100 years. Okay? It's very stable. It likes to spend time with itself. Okay? There's a positive ion sodium, there's a negative ion chloride, opposites attract in our formula unit here of sodium chloride, so it's very stable. What then would make it separate? This reaction is called a dissociation reaction. Okay. Association, dissociation. It's a dissociation reaction. Why? This stuff's really happy together. Water's perfectly fine by itself. Okay. There must be something about the interaction that is at least partially favorable, such that the solute can dissolve in the solvent to form our solution. Okay. And the answer, like so many things that in biochemical processes, comes down to electrochemical interactions. So I'm going to make an attempt to draw a little bit of a sodium chloride crystal. Luckily for you, I'll keep it fairly small. But we're going to have interspersions of positive and negative charges. Okay, so the purple has a charge, the green has an opposite charge, and then opposites attract. If you can picture this in 3 dimensions and extending a whole bunch of, a whole wide range of dimensions. As a quick review back from our bonding chapter and electronegativity, does anybody remember or can think back to which of the ions is the purple dot? Is it our positive ion or our negative ion? And which of the ions is the green circle? Well, to quickly review, the element chlorine has how many protons? Okay. And it's added an electron for a negative charge. The element sodium has how many protons? And it's lost an electron to make its positive charge. So the ratio of proton to electron in sodium is much greater. The sodium ion is right here, the purple dot, and our chloride ions are larger. The negative charge is larger, okay? Because there's relatively, as a ratio, fewer protons to pull the electrons close to it. Okay? Those electrons spread further out. That's why our negative ion is larger. Okay? Hopefully that little bit of review will help. Now, again, as I mentioned before, we're pretty happy together, pretty stable. Okay? There must be something about water then that is able to favorably interact. So if we can imagine a water molecule the oxygen atom has a special property in this molecule, such that it holds onto electrons more tightly than the hydrogen. So we have these little what are called partial charges, or water is a polar molecule. It's not a full plus and full minus, it's a slight minus and a slight plus. And as you could probably figure, the slightly negative oxygen is going to surround the sodium, such that our positive ion will be surrounded by our slightly negative oxygens in a solvent cage. This is how it works. There's enough oxygens, slightly negative, that surround the sodium ion to kind of coax it into breaking away from this happy crystalline structure, such that it's now surrounded here. Okay. So there's a couple elements in the process of forming a solution, what we made here. We have to have the solvent make room. The water needs to expand to accommodate this space. And then the ion needs to have a favorable enough interaction such that it can be broken off. Okay. This requires energy in order to separate the positive and negative ions. So if you go ahead and grab onto your salt water solution now, you'll see it's a little bit cold. Right? The formation of this solution has actually pulled some of the energy out of the water temperature, and that's why it's been cooled down. I said this was important in biological processes. Why is that the case? Well, now this ion is mobile. It's not stuck together here in a really slow vibrational state. It can go places. It can cross cell membranes. Okay? It can be transported through blood. So there's all kinds of options now for what this ion and associated other ions can do in biological processes that are so critical to things like energy production and metabolism and even respiration and breathing, transporting oxygen through the blood. Okay? So the properties that determine the solubility of something, these positive and negative interactions, have a lot to do with our lives. And this dissociation is kind of how it gets started. To wrap up, I'll leave you with something to think about, which is that if these ions had a +2 charge and a -2 charge, we wouldn't have hardly any dissociation at all. Okay? One example would be calcium carbonate. That's also a salt. Okay? The charge is +2, -2. That doesn't dissolve in water hardly at all. In fact, we can use it to build buildings. So the properties of solute and solvent go a long way to determining how much they dissociate and then what participation they may have in biological processes.